Let's now take a look at Ampere Circuit Law, which states that the line integral of H around a closed path is the same as the net current enclosed by that path. So we can write this in an equation by doing an integral around some closed path L of our magnetic field intensity dot dl. So of course dl is just our differential length along that path, and we're saying that that is equal to our enclosed current we'll call I enclosed. And so of course this seems very similar to what we talked about with charges when we were looking at Gauss's law. So similar to Gauss's law. And so what that tells us is that just like with Gauss's law, this is going to be more easily applied to situations when we have symmetrical charge distribution, or in this case symmetrical current distribution. So easily applied when we have symmetrical current distribution. And of course with Gauss's law we had symmetrical charge distribution, but of course here we're talking about currents instead of charge. So we have symmetrical charge distribution. And just like Gauss's law was a special case of Coulomb's law, our Ampere circuit law is a special case of the Biot-Savart law. So special case of our Biot-Savart law. And again, when we have that symmetrical current distribution, it's going to be easier to use our Ampere circuit law. And we're going to see that in some of the following videos where we take a closer look at we take another look rather at our infinite current carrying filament. And we're also going to look at some other current configurations which have symmetrical distribution. So similar to what we did when we looked at Gauss's law, we can play around with this equation up here a little bit. So let's apply Stoke's theorem to that equation. So we're going to apply our Stoke's theorem, which as you might recall is going to allow us to take this line integral and change it to a surface integral by changing that integrand from a divergence to a curl. So what we can say then, and so if you want a refresher, you can look on page 85 in the textbook. Sorry, not 75, but page 85. So this was back when we were talking about vector calculus. But we can say that our I enclosed, which of course we have above, is the integral around this closed path L of h dot dl. And using Stoke's theorem, we can say that that line integral is equal to a surface integral of the curl of h, so del cross h, dot ds. And so now note that that ds here, of course, is going to be the direction of this ds vector can be determined from right-hand rule. We put our fingers in the direction of our differential path, and our thumb is going to be in the direction of ds. Okay, so now we can sort of connect this to something else that we talked about previously. So remember in chapter 5 when we were talking about fields and charges in material space, we talked about a few different current equations. And so particularly in the textbook, if you look on page 179, what we said that the enclosed current in some region is equal to the surface integral of our current density J dot ds. Now, of course, this is very similar to this expression up here. We have two surface integrals. So we have this one up here and this one down here, both surface integrals over some surface ds. So what we can do is just equate those two integrands. So we can say that our del cross h is equal to our j. And so this is going to be our third Maxwell equation. So we have del, so the curl of h, curl of our magnetic field intensity, is equal to our current density J. Okay, and so again, this is our third Maxwell equation. And so just like with when we looked at Gauss's law, we had a differential form and an integral form, and so that's true here as well. So this form down here is our differential form, and then our initial equation that we started with is our integral form. So of course they're both saying the same thing, just slightly differently. And in certain applications, one might be more relevant than the other. And so we'll see that as we're looking at some of the current distributions in the following videos. So one thing to note is, unlike our electrostatic fields, our magnetic fields are not conservative, or our magnetostatic fields, I should say. So our magnetostatic fields are not conservative. And so the reason we say that is, of course, the curl of our magnetic field H, magnetic field intensity, is not equal to 0, the same way that we saw it was with our electric field. And again, that's just sort of some notation that you might hear thrown around. We'll talk more about the practical implications of that a little bit later on.